In this video, we will be discussing how to factor polynomials that we have started calling dots into its factors. Polynomials are when you have one expression that is held together with multiple terms. When we factor that expression, it is like dividing it into its parts that if you were to multiply them back together, would give you the polynomial that you started with. Remember that dots stands for a difference of two squares. And there we're talking about square terms or square polynomial terms instead of squares as in the shape. So you will be expected to apply your knowledge in class once we have a follow-up class for this video. Please pause and replay if needed. Remember, we've talked about what it takes in order for a polynomial to be a dots example. So remember, it needs to have three things. The coefficient of these expressions needs to have some sort of a perfect square number. So 16, 4, 36, 1, all of those are perfect squares, so those could be the coefficients, as well as the constants in that polynomial. So basically, all the numbers that you see, other than the exponents, have to be perfect squares. In addition to that, the exponents then, in particular, they have to be even. So they don't have to be perfect squares, but they have to be even numbers. Lastly, dots has to end up becoming a polynomial that had two terms that were held together by subtraction of two positive terms. So an example of a dots polynomial could be 4x to the 6th minus 36. Remember, you also can have an example that looks like it's addition, but if you were to rearrange it, you could easily write it as subtraction. So that would be an example like negative x squared plus 49. Although this looks like an example that is held together by addition, it's not held together by addition of two positive terms. Because if I were to rearrange this so that the constant came first, I would have 49 minus x squared. And now it is, in fact, looking like a dots situation. So now that you remember what dots are, what I would like you to do is complete questions A through I. Looking at each of these expressions, some of them are dots and some of them are not. What I need you to do is, if your example or your polynomial is a dots situation, factor it. So create those two factors that would have given you that polynomial. If it's not dots, state why it's not dots. So for example, if there is one with addition and you know that it's not subtraction of two positive terms, then you want to circle the addition symbol and say not dots because it's addition. Please pause the video while you complete A through I. Press play when you've finished all of your examples and you're ready to check your work. Okay, now that you've finished examples A through I, it's time to check our work. Once all of the answers are posted, please pause the video so that you can have time to reflect upon which questions you got right and which ones maybe you need to correct. I have highlighted all of the examples, A through I, that were not an example of dots. So please pause the video now, check your factors, and correct any mistakes that you might have made. So now that you're an expert at dots, it's time to move on to some new examples. Each of these four examples that I have for you down here are both examples of dots. If we look at this first one, I know this is dots because both of these terms are perfect squares and they're held together by subtraction. So if I were to follow the rules of factoring dots, I would know I need to take the square root of 4, which is 2. I need to split y squared in half so that now I just have one y in either side. I need my factors to have opposite signs, so one of them is addition and one of them is subtraction. And then I need to take the square root of 25. And the square root of 25 is 5. So do one more example of dots, now having a larger coefficient in front of x squared. Please complete the you do over here, pause the video, and then check your work. Now that you've completed the first you do, hopefully you should have gotten the factors of 3x minus 14 and 3x plus 14. It's okay if your two factors are in the opposite order. It doesn't matter whether the addition factor comes first or the subtraction factor comes first. Now moving on to another example, you're going to see how this example is slightly different. When I factor this, a lot of people forget that 1 is a perfect square, but in fact it is. So 1 times 1 is 1, which makes 1 a perfect square. Please don't forget that. So here, 81a to the 8th, I would split that up as 9, because the square root of 81 is 9. A to the 4th, because I'm splitting 8 in half. And then the square root of 1 is 1, so I have plus 1 and I have minus 1. So here, if you look at my factor, I have addition of two terms. So that factor looks pretty solid. But if I draw my attention over here to this factor, you're going to notice that here I have a perfect square, an even exponent, and subtraction. When I factored 81a to the 8th minus 1, I ended up getting one of my factors to also still be dots, which means I can break it up further. So I'm going to keep this factor that I can't break up there because it still exists. But now I need to take this factor and break it up into its two sections using the same idea. So this is going to be 3a squared minus 1 and 3a squared plus 1. So you're not technically done with dots until you look at all of the expressions you have and make sure that you still don't have a dots factor or a dots example. If I look, this one now has addition, so it should be done. This one has addition. This one has subtraction, so I should draw my eye to this factor. 1 is a perfect square. I have subtraction, but this squared is still even. However, 3 is not a perfect square. So I can't break this factor up any further. That is how I know I have factored completely. So this is actually my answer to factoring 81a to the 8th minus 1. So sometimes you have to keep simplifying. It's kind of like simplifying fractions. If I were to simplify a fraction and I could divide it by 2 or 4, but I choose to divide that fraction by 2, then I'm not simplifying it completely. These polynomials have the same idea. So see if you can do this second you do, keeping in mind the idea that you might be able to break your factors up and keep going. Pause the video, give it a try, and see how you did. Let's see how we did. So hopefully you were able to get m to the 6th plus 4 times m to the 3rd plus 2 times m to the 3rd minus 2. When I factored m to the 12th minus 16, that original polynomial, I saw that I got factors of m to the 6th plus 4 and m to the 6th minus 4. But then I noticed that this factor in particular still was an example of dots, so I needed to factor it further. That is how I got these two factors in blue of m to the 3rd plus 2 and m to the 3rd minus 2. I knew that I was finished factoring because this expression is the only one that has subtraction. It doesn't have an even exponent, and 2 is not a perfect square. So I knew I was done. So in order to factor dots completely, you need to make sure that you do the following. Here's our big ideas. To factor, you need to take the square root of your coefficients and your constants. So all of those numbers that are perfect squares, you need to take that square root. And you're going to put one of each of those numbers in those factors. You're also then going to split the exponents in half, putting half in one of the factors and half in the other. One of your factors should have addition, and one of them should have subtraction. So that's why they have opposite signs here. And the last thing you need to make sure that you do, now that we know that factoring can keep going sometimes, is you need to search for dots within the factors that you just found. Make sure that you can't keep simplifying it further. So keeping this in mind, you can flip to the back and see if you can factor each of those expressions correctly. I will be posting a key. In this video, you learned how to factor dots polynomials into their factors and making sure that you factor them completely. You will be expected to apply this knowledge in class.